Okay, so now I'm going to show you a general technique that is very useful to extract statistics and do comparisons when we are fitting models, for example, or doing some kind of adjustment like that. But before starting this lecture, I just wanted to clarify one small glitch on the previous one, because it was this part with the dictionaries. So if you create a dictionary with the usual way that we saw previously, when we use the curly brackets and then we put a key and a value, you need to use this notation. So this is one way of creating the dictionary. And if you create a dictionary for these purposes, where you want to specify the arguments for a function, you need to give these names of the parameters as strings. If you do it this way with the curly brackets, then you cannot do this that I was doing here. And that's what got me a bit confused, because I failed to notice that I was using the dictionary function from Python. So this is something that I didn't explain yet. And you have this dict function that creates a dictionary from the values that you give it. And you can give the keys here as names of parameters and the associated values by using this equal sign. So if you use the dict function like this, it will create keys with these names. So this will actually be turned into strings, but you don't need to send them as strings, and it will associate the values. So this one works correctly like this, but just remember that this is not the same as creating the dictionary with the curly brackets. You create the dictionary calling this constructor function that builds the dictionary. Okay, so having this clarified, let's go to bootstrapping. And the idea here is the bootstrapping is a method to resample our data in order to extract some statistics. For example, in this example I'm going to give is to estimate the confidence intervals for parameters. So we're going to look at the correlation between height and lung capacity in children and teenagers, and lung capacity measured by this forced expiratory volume, which is the volume of air that someone can expel when trying to, for example, fill a balloon or something like that. Then we're going to look at residual bootstrapping, which is a variant of bootstrapping using the an enzyme kinetics example. And I'm going also to show you this other function that you can use for fitting models that may be a bit more complex than the ones we used in curve fitting. Okay, so let's look at this example. We have this forced expiratory volume, which is how much air a person can blow in one single go when trying to expel as much air as possible. And we're going to look at this versus the height. So we have data on the lung capacity of children and teenagers. We have children 9 years old, 6 years old, and so on. We have the height, the volume for sorry, this is the volume, the height in inches, and we have also whether they are smokers or non-smokers. There are some teenagers in the sample that are smokers. But we're going to look at the sex, and the height, and the lung capacity. And we'll do just a simple exploratory analysis with pandas and NumPy, and then we'll jump into bootstrapping. So we're going to load the data. This is a CSV file. We're going to read it with pandas. We imported the pandas module as usual. And so we have here a data frame with all our data. We're also going to call this drop NA method of the data frame to drop all the rows that have missing values. Because sometimes you have data where values are missing, where we don't want those. We just want the rows where we have all the values. Now we're going to separate this into two data frames. So we want the rows corresponding to where the sex is male, and this will give us the male table, and the same thing for female. So now we have male and female being two data frames, one with all the data for female subjects and the other for male subjects. And now we can create a figure, and we can plot the data for male and female. And this is one thing that you can do when you are using the plot functions from pandas in the data frames. You can specify some axes where the plot will be drawn. So this way you can control where the different plots are drawn. And the way we do this is we create a figure. We use the get current axis from the pyplot module. This gives us a pointer reference to the object where all the plots will be drawn. And now we give this object here as an additional argument for the plot functions on these data frames. So this means that both plots will be drawn on that particular axis. So whenever you want to use pandas for doing your plots, but you want to specify in which figure they will be drawn, you can use this approach. And so you can still use pandas and control where the plot will be made. So we are going to use different colors, blue and pink for boys and girls, so following the stereotypes. Hope I don't get in trouble for this. But now we can see the distribution. So we have this cloud. This is the height and the lung capacity. And we see that lung capacity increases with height. This is expected. And we see that this is the set of values for girls and the set of values for boys. And apparently they seem to be fairly similar. But the question is, are there differences here? Can we spot any difference between these groups? And so we can try to fit a curve. This is not quite a straight line. It seems to be curving. So let's try a polynomial of degree 2. And we have these three parameters. So one parameter P0 multiplied by height squared, then P1 multiplied by height, and P2 as a constant. So this will give us this polynomial of degree 2 that we're going to use to fit. And we're going to fit one polynomial to each of these clouds, the boys and the girls. So the way we can do this is to use this polyfit function from NumPy, and we just give the degree of the polynomial, the x values and the y values, and this will give us the parameters, the P0, P1 and P2 that we have here. So we have the parameters for the polynomial for the boys and the parameters for the girls, and so we have these two polynomial curves. And now we can use, I'll use linspace here to go from the smallest height to the largest height with 100 points, so that I can draw the curve smoothly. And I'm going to use polyval, which is polyfit tells you the coefficients for the polynomial when you give the data. You give x, y, and the degree of the polynomial, and it returns the coefficients as an array. And polyval will receive the coefficients and the x values and computes the corresponding y values. So this is very practical when you're dealing with polynomials with NumPy, because you can just use polyfit and polyval to get your curves. So we are going to plot the male and female curves also on the same set of axes. So we're going to add to the same plot we saw previously, and here are the two curves. So this is a polynomial curve for the boys in blue, and this is the polynomial curve for the girls. Now we see that even though the two clouds of points have a large overlap, the curve seems to be different. But the question is this difference significant? Are there really differences in the way lung capacity is developing over time in boys and girls? Or does this difference just come by chance because the points are slightly more to one side or the other and they are not really significant? So how could we answer this question, if the curves are the difference is significant or not? Okay, so this is where we can use bootstrapping. One way of testing this would be to get a new sample of boys and girls and see if the difference between the curves remains. So we could do this for different samples. We could repeat the measurements, get a new group of volunteers, measure the volume, lung capacity, the height, and do this over and over again, and do this several times to see if the difference between the curves is consistent or if it changes too much and they really are not significantly different. But we cannot do that. So in practice, this is usually very difficult for us to keep repeating the same experiments and getting more and more data. However, with bootstrapping, we can pretend or we can simulate that we did this. So the idea here is that we are going to, from our data, draw a random sample of the data that we have with reposition. So you're going to select points at random, in this case boys and girls at random, and we're going to generate replicas by picking them at random the same number that we have individually. So if we have 100 data points, we pick 100 data points at random. Since we are picking at random with reposition, we're going to select some of them repeated. So some will be drawn 2 times, 3 times, things like that. And because of that, since we are creating replicas with the same number of points, some points will be missing. So on average, 2/3 of the original data will be in each replica, but 1/3 will be missing, and of those 2/3, some of them will be repetitions. This is because we are doing this at random. So what we are getting with bootstrapping is replicas of our data that are not quite the same as our original data, because some points are missing and some points are repeated, but they have the same distribution as our data because they are randomly sampled from the data itself. So this is something that we can use to pretend or to mimic what could happen if we repeated the experiment. So this is what we're going to do here. We're going to create replicas of our original data and then fit the polynomial and compute the curve for each replica. So this is the code here. We have the X and the Y values, in this case, the height and the lung capacity values, the number of replicas we want to create, and the degree of the polynomial to fit. So now, for each of these replicas, note here that I'm using an underscore as a variable for the loop, for the for loop, because I don't really care in which replica I am. I just want to use this to do this code, to execute this code as many times as the number of replicas specified here. For example, if the user specifies 500 replicas, I'm going to do this 500 times. And what I'm going to do is to create a random set of indexes. So this is a vector with values ranging from 0 to the number of points that I have. And this vector has as many random values as the number of points that I have. So this is the random vector that I'm going to use to resample my data at random. And now I'm going to create a replica of the X values and a replica of the Y values by picking those particular chosen values from my arrays. Now I'm going to fit the polynomial here, and I'm going to append the parameters to this list. So this list will have 500 sets of parameters for the polynomial if this function is run with 500 replicas. I'm going to do the bootstrapping for the male subjects and for the female subjects. So now what I did here is to compute the polynomial 500 times for 500 replicas of each group of subjects. And now I can look at the parameters and see how they are distributed. So I can do a kernel density estimate plot here with the using this pandas series to create the plot, because pandas has this kernel density estimate implemented. So I just transform the values that I have here for the parameters into a pandas series and then call the kernel density estimate plot. So I'm going to use the first parameter. This is the one for x squared in the polynomial for the male and female subjects. And I'm going to draw the kernel density estimate for them both in the same figure. So I'm again using this axis from the figure to specify that I want them drawn in the same graph. So here we can see the distribution of that quadratic term in the curve for the female subjects and for the male subjects in these 500 polynomials computed by bootstrapping. So when I resample my data, I get different polynomials, but the parameters are not overlapping. So the parameters for the quadratic term are not overlapping, for the linear term are not overlapping either, and for the constant term also not overlapping. So we can see that the differences in these curves seem to be significant for this data. It's not just a matter of by chance having some points more over here or more over there. If I do these replicas by bootstrapping, by randomly sampling from my data, I get a consistent difference between the parameters of these curves. So this is one example of using bootstrapping to look at the interval, the range of the parameters we can have, and this way try to figure out if how significant something is, how uncertain the parameters are. So in this case, how significant the difference between the curves is with respect to the margin of uncertainty in the parameters we are determining. So let's see just a variation of bootstrapping, because sometimes we cannot use this vanilla bootstrapping just by random sampling, because sometimes it makes no sense to resample at random. For example, consider this problem here. We have this Michaelis-Menten expression for this type of kinetics, which is the initial velocity of the reaction of some catalytic reaction, some catalyzed reaction, so with an enzyme and a substrate, depends on the concentration of the substrate at that initial point, and these parameters of the enzyme, the maximum velocity of the enzyme, and the half point or the concentration of the substrate where the velocity will be 1/2 of the maximum. So these are characteristics of the enzyme, and we can try to estimate these values by doing an experiment where we change the concentration of the substrate, for example, 1, 2, 5, 8, 12 in some arbitrary units, and we measure this initial velocity for each of these concentrations. So we get something like this. For example, we have our data here where we have the concentrations of the substrate and we measure the initial velocity in each case. So in this kind of experiment, it doesn't make sense to draw a sample at random from our data because we chose the values of the initial concentrations. Note that in this other example, we were not choosing the height and the lung capacity of the subjects. This was given to us by nature at random when we sampled those subjects from the whole population. But in a case like this, the actual velocity may be due to some things nature is giving us, but the concentration values, we chose them ourselves. So this is where residual bootstrapping is useful. Instead of resampling the whole data, we are just going to resample the errors, that is the residuals between the best curve that we can fit and the actual data. So each data point will differ from the predicted value by some amount, and we can assume that these differences are due to some random factors and they all come from the same distribution. If we assume that, then we can resample these differences, these residuals, by just picking them at random and assigning them at random to different points. So let's see how we can do this. We have this model here. We want to adjust first this model to our data by minimizing the quadratic error. So you can do this by taking the logarithms and linearizing this, but we can do this directly. If we are working with Python, it's easy to do this directly just to minimize the quadratic error between the prediction and the actual measured initial velocity. So this would be just writing our function. So if we have a set of values for the substrate concentration and the parameters for our curve, so this Vmax and Km, we can compute what would be the predicted initial velocity for each concentration value. So this S is an array of the concentrations, for example, this array here. And this V will be an array, this pred here will be an array of the initial velocities predicted for all these concentrations. We multiply the Vmax by S, so Vmax is the first parameter here, and we divide this by Km plus X, Km is the second parameter. Now the error here, or the cost that we're trying to minimize, will be the sum of the square of the differences between the velocity, the actual velocities that we measured, and the predicted velocities. So the reason for using the sum or the mean quadratic error, it's the same thing in practice, is because this is the maximum likelihood solution if we assume that this error is normally distributed. So basically, minimizing the quadratic error is a very common approach when we're trying to fit these kinds of models, because it's just the assumption that we have a normally distributed error on the variable that we're trying to predict. So this is the function that we want to minimize. We want to adjust these parameters so that the quadratic error is as small as possible and our curve adjusts the data as well as possible. So to do this, now note that I should be testing the functions, but I'm going to skip that to make this faster. But remember that when you are writing your code, it's always a good idea to test each function individually. Otherwise, when you put everything together and you have some error, then it's much harder to figure out where the error occurred. Whereas if you test each function individually, you can always spot the error exactly when it appears in each of the functions. So now we're going to use this minimize function from optimize. This is a more powerful version of the curve fit, because it also allows you to give the function. Whatever arguments you want, you can send to the function that you're going to minimize, and you give an initial guess for the parameters. So this 1 is an initial guess for the Vmax and Km. It doesn't need to be very close to the actual value, but the closer it is, the easier it is to find the correct value. But what this does is gives the initial point where the minimize function will try to go down the cost function, the function to minimize, until it finds the best parameters. And these are the additional arguments that we can send to our function. So our function will receive a vector with the parameters to optimize, plus any additional arguments that we want to send it. And we can also set up bounds for the values we want to optimize. So for each of the values we want to optimize, we can specify a tuple that has the lower and the upper bound. In this case, the lower bound will be 0, because it doesn't make sense to have negative values for these parameters, so we cannot go below 0. But we are not going to give an upper bound, so you can put none there, and so there is no upper bound. They can go as high as the minimize function needs. And we do this both for Vmax and for Km. There are other things that you can do here. You can give a function that computes the derivatives and so on to make this more efficient. If you have very complex models, then you should really look up the documentation, the different optimization methods and so on, because it may be necessary to squeeze more performance out of this function. For this particular example, is not a problem, so this works like this. Now this minimize function will return a result object that includes information on what the remaining error is after minimization, how many iterations it did, and so on. But there is this X field that contains the best values for the parameters. So basically we are going to unpack that into Vmax and Km, and we get the best parameters for fitting our model to the data. So now we can do the plot. We can create, again, note the same idea, creating a number of values of X so that we can draw the curve smoothly. This goes from 0 to the maximum data plus 10%. So I multiply by 1.1 so that my line doesn't stop on the last point but goes a bit farther. These details you can customize as you like when you're doing your plots. Now I'm computing the Y values by writing the expression based on these X values, so X times Vmax divided by Km plus X, and I create the figure, plot the line, and plot the data here with these blue crosses, with this size of the marker and the width of the marker and so on. So this is the image that we get. These are the data points in blue, and this is the best curve that we have with Vmax of about 73. So this would be the limit here, asymptotic limit of this curve, and the Km 3.4, which is the concentration of substrate that gives us half the maximum velocity. So these are the two parameters that determine the shape of the curve. Okay, so now the question is, how confident can we be of these values, and what is the margin of uncertainty, considering that our data is not exactly on the curve? There is some error here, so maybe there is some uncertainty on the parameters. And we can compute that by residual bootstrapping. So what we're going to do is we're going to compute the residuals, which are the differences between the predicted values, which are in this curve here, and the actual values in our data. So these red lines give us the residuals for these points. And we're going to assume that these residuals are due to some random noise, and they all come from the same distribution. So this point is above the curve, but it could be below. This one could be above. This could be right on the curve. This one could be farther from the curve, and so on. These residuals are representing the kind of errors that we can expect to have if we repeat our experiment. Of course, it takes a lot of work to repeat the experiment, so we're not going to repeat the experiment. We're going to use bootstrapping to imitate repetitions of our experiment. So this is what we're going to do. We're going to create replicas by starting from the predicted curve and adding randomly picked residuals to the curve. So for exactly the same values of substrate concentration, because these are not random, these were chosen by us, we are going to compute new possible or plausible values for the measured initial velocity by picking residuals at random and adding them to our curve. And now we're going to compute the curve for each of these. So we can compute different sets of parameters depending on the replicas that we get in residual bootstrapping. And this will give us, again, a family of parameters for all of these curves. So this is the code for residual bootstrapping. We have the number of replicas here, the initial parameters for our curve, Vmax and Km. So this is the best model with the initial data and the data that we used. So now we're going to create our predictions. So the curve that serves as the baseline is using these parameters here with the values of substrate concentration in our data. So our data is a matrix that has the concentrations in the first row and the initial velocity values in the second row. So this is the prediction for all the different concentrations, and these are the residuals. The residuals are simply the actual values on the data minus the predicted values. So these would be these red lines here. And now for each replica, we're going to create a random set of indexes that is going to index all the elements here that we have, but we are going to pick at random from the residuals. So the replica will be based on the best curve. This is the best line here, but then adding random residuals, randomly picked residuals from all the points. So if in this position we happen to have picked this residual, then the point here will be below the curve over here. If in this position we happen to have picked this residual, this point would be higher, and this is what is generating all these different sets of points. So now we're going to call the minimize function on our cost function, on the error function that we are minimizing, and we obtain a set of Vmax and Km parameters for this particular replica. So we're going to append that to our parameters list and then return this as a NumPy array, a matrix which has on the first column all the values of Vmax computed for all the different curves, and on the second column all the values of Km. And now we can compute the mean. So you see the average here is 73 and 3.5, so approximately what we had, but we also can compute, for example, the standard deviation, and we see that there is a significant standard deviation for these values. So if you want, you can look at the different curves, because we can actually plot all of these curves, and this gives us an idea of the spread of the curves that we are creating when we use bootstrapping, residual bootstrapping on this data. And we can also draw, for example, the histograms of our parameters. So this gives us an idea of that on average the maximum velocity seems to be 73, but it ranges from about 60 something to almost 85 in this distribution. So this gives us an idea of the uncertainty margin for this parameter, and the same thing for Km. Okay, so to sum up, bootstrapping is the kind of thing that would be very impractical to do if you are using Excel or doing by hand or something like that, because you need to create lots of replicas and fit your models, for example, to lots of different replicas. But it's very easy to implement with programming, because you just do a loop and you repeat the same thing over and over, and you collect the parameters, and you get an idea of the margins, the ranges. Sometimes you cannot use the vanilla version of bootstrapping because your data is not completely random. For example, in that enzyme kinetics example, we were selecting the concentrations of the substrate, so it wouldn't make sense to replicate that experiment with data that had two times some concentration and another one missing or something like that at random. So in that case, you can, if you assume that the errors, the random errors, are coming from the same distribution, you can just resample the residuals and create your replicas by resampling the residuals. So this is a very practical way of getting an estimate of the uncertainty of your parameters or some other statistics that you want to gather in your model. So this is not something that probably you were intending on using when you came into this course, because you had specific problems for automating the processes that you are already using. But I would like also to, at the end of this course, give you some ideas of new things that you can do that go beyond what you were already doing with spreadsheets and so on. So next week we're going to look a bit at machine learning, just a very brief overview, because this is a field that is rapidly growing. You have very powerful tools for clustering, for classification, regression, and things like that. And they are very easy to use with the libraries that you have if you know a little bit of Python. For this week, I still did not have time to get the lecture notes ready, but the homework exercise, so the mandatory exercise for this week, is just to use the same data set that I showed you with the children and teenagers and the lung capacity, and replicate the same kind of approach that we are seeing here, but instead of comparing boys and girls, compare smokers and no smokers. So ignoring sex differences, just the group of people who smoke and don't smoke, and see if with bootstrapping you can decide if the parameters are significantly different or not. Okay, so for the final assignment, at this moment we are no longer looking at basic things of Python, so you have time to go back to whatever you might have still some trouble with and review that subject matter. For next week, I'm going to talk a bit on machine learning in the lectures, but then we are going to be dedicating the tutorials for the final assignment and for any revisions that you need. So what I propose is that you start thinking about what you want to do in the final assignment, and we can have some discussions about that, about the details, so that in these next 2 weeks, this one and the next one, you get started on the project, and then it's easier for you to continue on your own. Okay, so I'll just log into Colibri and start the Zoom meeting. We can all meet there.